All right, next we're going to head towards geometric series. But before we talk about geometric series, just wanted to mention this theorem one, the linearity of series, which we can essentially think of convergent series. So if each of these two series are convergent, so they converge, then if you add or subtract them, the terms together, you will obtain a new series. Or you can also multiply either one of them by some constant, any constant, and these two new series that you obtain will also converge. So these series here will converge. And this doesn't have to be a sub n, it could have been b sub n. Essentially, if you have a convergent series, you can multiply it by a constant and that new series will still converge. And if you have multiple convergent series, if you add or subtract them in any way or multiply them, you are guaranteed to have another new series that also converges. But what's interesting here is if you have a series, like let's, instead of pretending that we started with two independent series, let's just say we have a series like this, and that series converges. If you split it up into two series, one or both of those series may not converge, which is interesting. So you have to be careful when you're working with these. Okay, theorem 2, we talk about a geometric series. So we've already encountered a geometric series. From an earlier example, we took a look at the series from n equals 0 to infinity 1 over 2 to the n. This is a geometric series because it can be written in the format as some number, so a constant, times another constant raised to the nth power. In this case, that constant is 1, and the other constant that is being raised to the nth power, that is a half. So really, it's 1 times a half raised to the nth power. That is our series right here. Whenever your series can be written in this format of a constant times another constant raised to the nth power, then that makes the series, we classify that, we name that a geometric series. So a geometric series does converge. Specifically, it converges to c over 1 minus r, but this is specifically when we start with n, the initial value of the index being 0. If the initial value of the index is something other than 0, so let's say we start at some arbitrary value k, then the series converges to this, cr to the k over 1 minus r. So more commonly than not, it's easier to think about it written this way. The sum of a geometric series is the first term of the series. Notice the first term here is c, so we have c. First term of this series is cr to the k, and that also appears here. So it's as if we could just say the first term divided by 1 minus r. And this r is called the common ratio. The common ratio. Okay. So let's backtrack just for a moment and actually take a look at the hypothesis here. So if the absolute value of your common ratio, this another constant, this is our r, common ratio. If your common ratio in absolute value is less than 1, then it converges. If your common ratio in absolute value is greater than or equal to 1, then it diverges. It diverges. So that's this part right here. So there's a proof of it here. But we will move on to an example. So Example 4, evaluate the series from n equals 0 to infinity of 0.6 to the n. So this is a geometric series because I can write this expression in the format of a constant times another constant raised to the nth power. So this means our common ratio is 0.6. Or I like fractions better, so let's go ahead and do 3/5. So I'm just going to rewrite this. N equals 0 to infinity of 3/5 to the n. So our first term of the series is 3/5 to the 0th power, which is 1. So 1 plus 3/5 plus 9/25 plus so on and so forth forever. So because 3/5 is positive, the absolute value of it's the same, but what's important here is that this is less than 1. Because it's less than 1 in the absolute value, this means that the series converges. And since it's a geometric series, we can easily say the value to which it converges, which is the first term of the series, which is 1 in this case. Just grab that first term, divided by 1 minus the common ratio. So 1 minus 3/5. So this is 1 over 2/5, which is exactly 5/2. Okay. Let's take a look at example 5. Determine if the following series 1 plus 0.4 plus 0.16 plus 0.064 plus so on and so forth. Determine if this series converges. So let's go ahead and just say that this right here appears to be, notice that 0.4 is the same thing. 0.4 is exactly the same as 2/5. 2/5. And 0.16 is exactly 0.4 squared. So that's exactly 2 to the 2/5 squared. So this is 4/25. Similarly, 0.064 is 0.4 cubed, which is, well, 2/5 cubed. So 8/125. So for all of these, it does look like we have a common ratio of 0.4, or if you write it as a fraction, 2/5. Okay, so we could write this more compactly as a series. N equals 0 to infinity. This would be 2/5 to the n. We already know our first term of this series is 1. And because we can write it in this format here, we know that the series is geometric. And a geometric series converges to the first term divided by 1 minus the common ratio. So this is 1 over 3/5, which is 5/3. Okay, example 6. Taking a look at this one is a lot less obvious what to do with it. A lot of these questions and these examples, they're going to require some algebraic rearrangement, some sort of manipulation, some sort of simplification, maybe splitting things apart, maybe combining terms in order to make it look like a series that you can recognize. Now, so far, the only series that we can recognize, at least classify by name, are telescoping series and geometric series. So a telescoping series either is presented as a sum/difference of rational expressions, or it is presented as a single rational expression. This is not a rational expression because we've got the index of the series appearing as an exponent. So it can't be a telescoping. So that leaves the only choice, well, I guess technically two choices remain. It either is unclassifiable, at least based on what we know so far, or it's geometric. So if it's geometric, that means it is possible to put it in the form a constant times another constant raised to the nth power. So let's remind ourselves of this. So I'm just going to copy down what we kind of said, which was that this isn't telescoping. I guess I'll say a telescoping series. Not a rational expression. But could be geometric. And we know a geometric series can be written as the series from some starting value. So I'll just say k. It doesn't matter what the starting value is, really. At least as far as it doesn't matter for classification purposes. A number times another number called the common ratio raised to the nth power. So can I take this expression and get it into that format? Okay. Well, the first thing I'm going to do is I want this raised to the nth power, a single number raised to the nth power. So I'm going to go ahead and notice that this 10 to the n over negative 9 to the n plus 1, I want my exponents to be the same. So there's an extra copy, there's one more copy of negative 9 than n copies. It's n plus 1 copies. So I can break this apart into negative 9 to the n times a negative 9. There's the 1 copy. I just split it apart. So this 10 to the n and this negative 9 to the n, they are two numbers that have the same exponent. So I could sort of rip that apart in a certain way. Specifically, I'm going to, let's make the negative 1/9, let's make that a separate thing, and then we'll have 10 to the n over negative 9 to the n. I just took this negative 9, it's in the bottom, so technically it's a negative 1/9, and I just pulled it out front. So I split my fraction into the thing that doesn't have a power of n and the things that do have a power of n. Then I would go ahead and write this as a single number raised to the nth power. Okay, so we have now successfully rewritten this into the format of a geometric series. So this series here can be written as, from n equals 0 to infinity, negative 1/9 times negative 10/9 to the nth power. And this series will diverge. This diverges since the common ratio is negative 10/9. And the absolute value of this is greater than or equal to 1. That's our justification.